Yeah, so I'm going to talk about composite materials, basically. Composite materials has a long history. It's sort of interesting too that
Recording in progress.
Before the idea of atoms and things like this, people like Faraday and Massotti thought that ordinary dielectric materials were actually composite materials consisting of metal spheres in a air or something like this, you know. And anyway, so this is okay. Joint work with many collaborators. I'm not sure. Let's see. This, so maybe it's this one. Oh. Okay. Yeah. So yeah, many collaborators here. I won't go through all of them, but Yuri Gorosky is here. Owen Miller's here. Miha Pudina gave the talk, and Christian Kern was here earlier. And in particular, I want to thank him for sharing many slides and images here. So what sort of composite material we're talking about? This is an example. So basically, it's a layered material, but it's layers within layers. So it's sort of a hierarchical layered material. So basically, you have some hat, you put two materials or more in the hat, and then take them out and sort of layer them together, put them back in the hat, and you keep on this process. But one key thing is that there's always a separation of length scales here. So ideally, whoops. So let's see. Maybe I have to use this. Yeah, okay. Good. Okay, all right, good. So we've got layering here. The layering here should be much smaller than this sort of more macroscopic layering. And this is the outline of the talk. One is, so we're talking about Herglotz functions and Stiltes functions. And so I'm going to talk about mimicking effective conductivities of laminates using effective conductivities of arbitrary composites using hierarchical laminate materials. Okay, yeah. And so, yeah, okay. Doesn't seem to work. Okay, thanks, Mixed. And anyway, so the second thing is I want to talk about is the connection between what are called exact relations in composite materials and lamination, and that's a subject that Yuri is an expert on. And then talking about laminates to achieve any possible elasticity tensor in 2 dimensions. And lastly, I was mentioning a little bit about reversal of the sign of the Hall coefficient, which is a surprising thing. So this gives you sort of an idea of the range of problems that are equivalent to electrical conductivity with the fields J, E, and sigma taking different meanings according to the problem. So in those problems, basically, you've got this constitutive law that J is equal to sigma E, div dot J equals 0, and E is equal to grad V. And then it's you look for periodic solutions. When the conductivity is periodic, you look for fields that are periodic. And then it's a relationship between the average current and the average electric field, which determines the effective conductivity according to that formula there. And I'd emphasize that tensity, that matrix, if you like, sigma x and sigma star, are not necessarily symmetric. And that's true if there's a magnetic field, but it's also true for convection-enhanced diffusion. And then, of course, one may ask about a lot of other physical problems, and here I've listed some of them, you know, elasticity, thermoelasticity, poroelasticity, etc. Basically the same format holds for them as well. So I won't be saying much about this. Aaron Walters, I think, is going to talk a little bit more. But basically you have a Hilbert space where there's a decomposition into three orthogonal spaces. And then you've got some operator L mapping the Hilbert space to itself. And usually it's got some sort of coercivity properties and boundedness properties. And then you look for solutions to J is equal to LE, where J is in the span of U and calligraphic J, and E is in the span of U and calligraphic E. And then the effective tensor is basically defined by the projections of J and E onto U. But I won't be saying much more about this abstract things, but I will come back to these gamma operators a little bit later. Anyway, this is the simplest laminate, of course. It's just a simple slicing of two materials together. And then you have the conductivities of, say, two materials. And if they're crystals, they may have different conductivity in the different directions. And so the lambda 1s and lambda 2s and lambda 3s are then those eigenvalues of them. If they're aligned in the direction of lamination, then basically the effective conductivity is an arithmetic mean in the transverse plane and a geometric mean in the direction of n. And so here we're laminating just two materials together, but I could actually laminate two composite materials together. And each of those will, if you like, have their Stiltes or Herglotz functions. And it has been discussed that, of course, if we add two Herglotz functions together, we get a Herglotz function. And as Christian pointed out, also it's true if we take the reciprocals, then the sum of the reciprocals is basically a Herglotz function of the inverse of z, this is basically says that you sort of stay within the same class of functions when you laminate, as you'd expect. One of the simplest lamination schemes, which sort of show what one can get, is something Schulgasser came up with in the late 70s. And actually, I thought this was the first example of someone using these layered materials. But using variational principles, it's sort of easy to see that the effective conductivity is bounded above by the mean of the conductivity. Oh, thank you. What? Oh, sorry. Okay. Yeah. Whoops. Yeah, so the question is whether you can realize that upper bound. In particular, that upper bound implies that if you've got some isotropic polycrystals, so you've got grains at different orientations, but macroscopically it's isotropic, that tells you that the conductivity, the effective conductivity, which is now a scalar because you have the same conductivity in all directions, is nothing else but an arithmetic mean of the eigenvalues of the conductivity tensor. And actually, Schulgasser proved the upper bound as the idea is to sort of rotate the material so that in the direction n, which you laminate, which is you expect a harmonic mean. Of course, if the conductivities are equal there, the harmonic mean is actually the same as the arithmetic mean. And so the effective conductivity then is just an average. And you just repeat this process. So first you mix the two in that direction in equal proportions, and you get an average of those two, and then you just repeat it a couple more times until you get what you want. And this is sort of known as a rank 3 laminate. So the idea of rank 3 is the number of steps of lamination that you actually require. And actually, this is sort of you can actually get by with a rank 2 laminate, but that's only true if the moduli are real and not complex, because the volume fractions depend upon the moduli, and if they're complex, you have a problem with complex volume fractions. And I just mentioned that you sort of get hierarchical laminates that are sometimes sort of self-similar, but self-similar, and then you have sort of rotations. So if you're interested in the lowest conducting polycrystal, it turns out to be sort of something like this. This is for elasticity in 2 dimensions. So actually, I sort of found out from John Willis that he suggested, you know, when I mentioned Schulgast and laminates, he said, well, you should look at Maxwell. And sure enough, Maxwell had actually come up with this a lamination scheme, which is a hierarchical laminate, in connection with the formula at the top. Maxwell's interested in conductivity, but this is the formula for dielectric materials. And that has a long history as well. There was a lot of discussion about its validity. Rayleigh actually solved for a periodic array of cylinders or spheres, and actually proved this in the low volume fraction limit. So this is sort of applications, as it explains the sort of unusual properties of the Lycurgus cup. So depending upon whether the light's inside or outside, it looks green or red. And so there's sort of an older paper. This is 1904 by J.C. Maxwell Garnett. It's sort of odd, he's Maxwell too, but apparently Garnett was the laboratory assistant of Maxwell, and Maxwell was so impressed that, Garnett was so impressed that he named his son after him. And so then it's sort of interesting that he sort of carried on in electromagnetism. So this paper explains the colours of stained glass windows in terms of the metal spheres and things that are embedded in them. So gold embedded in glass gives you a red colour. And not chemically, it's just due to the resonance. It's due to the fact that the denominator becomes very small. And Hashim then, in the 1962s, come up with a very nice argument that showed that this formula here was actually, and this is equivalent to the formula that I had before, but this is for conductivity, that it was actually exact for this composite material up the top. So that's actually the sort of 2-dimensional version, but it should be spheres stuck together. I'll come up with another one. So this is actually from Christian Kern. And so we've got this sort of coated sphere assemblage at the top on the left, and the Maxwell construction, which gives exactly the same formula, is this sort of laminate of laminates. In 2 dimensions, you get this other sort of laminate replacing coated cylinders. So these have exactly the same properties and attain that formula due to Clausius-Massotti and Maxwell and things. And so that's associated with a laminate. There's sort of a tree structure. And so as you get up this tree, you know, at the bottom you've got materials 1 and 2 on the left. You combine them in different volume fractions, where F1 and F2 are the desired volume fractions, or F1 is the desired fractions of phase 1. So they add up to 1 at each level. and the X, Y, and Z sort of tell you the directions of lamination. So that's the story. And then, of course, you can have doubly coated spheres, and then you get continued fraction for this effective conductivity. So what's nice is that if you've got coated spheres as opposed to the single spheres that in stained glass windows, you can get a continuum of colours actually. So that's nice, and that's Naomi Hallis's group in 2002. So basically, the effective conductivity, we can put sigma 2, the conductivity of phase 2 equals 1 because it's a homogeneous function. And so in a two-phase composite, the effective conductivity over sigma 1 is actually a Stiltige function. The effective conductivity as a function of sigma 1 has a potential poles and zeros on the negative real axis, so it could have branch cuts. And, so myself and David Bergman and Golden Papanicolaou and Ken Golden's here were involved in developing that correspondence between and analyticity of the effective conductivity as a function of the component conductivities. So sort of more generally, you could have a multi-phase material, which is sort of a function of parameters Z1 over Zn, and then there's some sort of normalization. And so the Z1 up to the Zn could be the individual conductivities of the phases, and that has then this Herglotz property that the imaginary part of that tensor L star is positive semi-definite if the imaginary parts of the Zi are positive. And sort of more generally, you may actually have some sort of polycrystalline material where the tensors are matrices. The properties of the phases are tensors, which would be represented by matrices, and then the properties sort of carry through, and in particular the Herglotz property carries through. The second property is if you've got a polycrystalline material where you've got the same crystal in different orientations, the second property is only true if L naught is rotationally invariant. So if we look at the conductivity in just one direction, in the direction E naught, we've got an electric field there, then applying that lamination formula, you get a representation formula for, so this is just of a laminate material in the parallel direction, in the direction of E0, and it's given here by this is a harmonic average because in this region here, we've got layers which are perpendicular to the field, and so we get the harmonic average here, and then we've got different layers here with a different value of Q, which is the proportion, and so they're weighted by, it's just an arithmetic average, and so they're weighted by constants A alpha. And then there's, in two dimensions, there's a nice result due to Keller and Mendelssohn and others, is that the conductivity in the perpendicular direction is given but just by this formula in terms of the parallel direction. So actually, any functions that satisfy for any material, then if we just look at the one of the diagonal elements of the effective conductivity tensor, it exactly has that formula. Okay. Okay. Yep. Okay. So actually, yeah, so that's basically what it said. Any two-dimensional microstructure, in particular if it has reflection symmetry, can be modeled by a laminate geometry. And in particular, if it's an isotropic material, it has that property. Okay, great. Yeah. Yeah. Yes, so alternatively, you can use multi-coded disk geometries. So I've mentioned the doubly coded ones, but you can have triply coded ones and so forth. And then you can alternatively use these geometries to represent any geometry at all in 2 dimensions. And then it's basically an inductive procedure. If you put the conductivity of the grey material equal to 0, you can sort of determine the volume fraction of the outermost layer, and so you can sort of peel that away, and then you do the same thing with the effective conductivity of an arbitrary geometry. But actually, if we consider other sorts of geometry, it's clear that the eigenvectors of the effective conductivity can actually rotate as far as sigma 1 and sigma 2 plane. If I have a low contrast between my 2 materials here, things are going to be dominated by these ellipsoids, and so the eigenvectors of the conductivity tensor will be in those directions. But if the conductivity is very large, the current is going to flow along these lines, and so you have a different orientation. And then you can prove that actually a hierarchical laminate scheme actually suffices in 2 dimensions to mimic any possible response of any composite material. That's sort of a generalization of that relationship that I had before. And actually, you're going to sort of carry through the analysis to polycrystals in 2 dimensions, where you have polycrystals of different orientations. That you have an arbitrary polycrystal, and then you can model it by this hierarchical laminate material. And this correspondence is actually made at the level of the Hilbert space, and you don't actually deal with the conductivity functions, because here actually you have 2 scalar conductivity functions, each of 3 complex variables. And so that would be sort of hard to handle using complex analytic techniques and things. So, in 3 dimensions, it's not clear. We have this inequality that sort of holds for isotropic material, but we don't know if hierarchical laminates sort of suffice to achieve the properties. However, one gets an idea of how difficult the problem is if you just look for geometries that have a simple pole. You know, the simplest type of analytic property function, just or Stiltz function you would like. So these functions with a simple pole come up in one context, and that's the context of bounding the effective dielectric constant of a composite material when that composite material is isotropic. And so now you have the real and imaginary parts of the dielectric constant, and you have this lens-shaped region within which the effective dielectric constant lies. And this upper curve here just corresponds to an analytic function with a simple pole. And so the question is can you find laminates that trace this boundary as the geometry varies? And so that's what we're trying to achieve here. The only free parameter here is u. F1 and F2 are the volume fractions of the 2 phases. This factor 3 comes in because you know the second derivative. But obviously this just has a single pole, and so a long while ago I sort of realized that if you take these geometries here and you apply Schulgass's construction, you got actually points on that bound. So that's what I had sort of found. I actually thought that they were all the points. So this was joint work with Christian Kern and Owen Miller, and Owen's here, is that so Christian found that there were actually additional points on this curve here. Basically there were two types of structures that he found. First of all, I guess these, when you look at other laminate geometries, you can actually come very, very close to sort of achieving that bound. And the other bound, we found bound on the other side given by this red line, that was corresponds to a doubly coated sphere geometry. And that can be mimicked by laminate materials. So this is one of the ones that Christian found that just has one pole, and so it's given by this tree structure. Actually, it's just part of this tree structure because at the end, you have to apply the Schulgasse structure. So there's two more layers of the tree. And they've, at each of those, there's sort of branches sort of coming down. So the tree structure is sort of quite complicated. And the other structure Christian found had this laminate type structure. And so it's still an open question to prove or disprove whether you can get other points which are attained. I think Christian felt the answer was no. And then there was this new bound. So now I want to talk about laminates and the theory of exact relations. So the idea of exact relations is that there's some sort of manifold when you have two tensors, L1 and L2, and these could depend on the property that you're considering, that you've got some sort of manifold, and if the effective tensor always lies on that manifold, then you call this an exact relation. And so in particular for conductivity, you have the property that if you take your manifold as conductivities with constant determinant in 2 dimensions, then the effective conductivity shares that same determinant. And okay, this is a list of, maybe I missed some, but a list of all the people that obtained exact relations. And so Yuri Grabowski beat them all because he discovered hundreds. And anyway, and then Yuri wrote this book that discusses a lot of these. And then also in my book, I had a number of chapters sort of devoted to that topic. So the first idea, or the first breakthrough, was one that Yuri realized, is that if an exact relationship holds for all geometries, it must certainly hold for laminate geometries. What's sort of interesting is there's this sort of fractional linear transformation that depends upon this gamma operator. So this is in Fourier space now. When you take the Fourier transform of the gamma operator, it becomes something local in Fourier space, only depending on the Fourier vector k, but this is now n, the direction of lamination. But what's nice about this formula is that it converts lamination into a linear average. And so the point is that you've got this manifold, which is all curved and things. If you do this transformation, you necessarily must map it to a flat space. Because when you laminate two materials together, you're taking a linear average here, and the only manifold which has got codimension greater than or equal to 1 is a subspace. But this is sort of a nonlinear transformation, depending upon the direction of lamination. And so if we take a different lamination, one also wants that to end up in a linear space. So that implies that this sort of composition, which is a nonlinear transformation, maps the subspace to a subspace. And so then it becomes a question of what subspaces have that property. And so you do the expand that transformation. The first thing you notice is that from the linear term, the subspace doesn't depend upon the direction of lamination. And then from subsequent terms, you find out that they all lie in the subspace if just this second order term lies in the subspace. So you have this sort of condition on your subspace K and this A of M just depends upon these sort of gamma operators. So this is something you know according to the problem under consideration. And so in particular for the conductivity example, A of M takes this form, and the exact relationship holds because the product of three trace-free symmetric matrices is also trace-free and symmetric. So then you can sort of apply it to many other problems, and that's what Yuri did. And so it becomes an algebraic problem, but a difficult algebraic problem. Following Yuri's work together with Dane Sage, we obtained the proof that if you want the manifold to be stable not just under lamination, but under any homogenization, mixing any materials, any geometry, you've got a slightly different condition on your subspace. So M minus gamma n, that could be the A of n before. So this should be A of k here. It looks more or less exactly the same as the ones for laminates, except you've got a K1 and a K2, whereas before these were the same. So there's a slightly different condition, and you researched for a long time and always seemed to be the case that if the first condition was satisfied, then this was condition 2. But actually, he came up with an example with using quaternions that showed that they were actually different in some cases. Now I want to talk about generating, using laminates to generate properties that are surprising and quite unlike those of the constituent materials. So basically metamaterials. In particular, using laminates to achieve any possible two-dimensional elasticity tensors. So basically, if I take the landscape of isotropic materials, they're dictated by their bulk modulus and their shear modulus. And roughly speaking, you could put them into categories of very spongy materials, rigid materials, rubbery materials, materials that are difficult to compress but relatively easy to shear. And this corner here, one has basically sort of dilational materials or auxetic materials that are easy to compress but hard to shear. So if you're in 2 dimensions, this would be a beautiful way of using conformal analytic transformations. You know, that would be the only easy deformation of this sort of material. Sort of back in 1987, Roderick Lakes built this sort of foam that had this sort of property that when you pulled it, it got fatter rather than thinner. And so this was one of these materials which was auxetic or dilational, and it had been a big debate as to whether they actually existed. And then so I found this sort of more concrete example. These are sort of parallelograms. This is sort of rigid material. The only easy deformation of this is a dilational. And there's this other structure of Graeme and Evans, which is also closely related to one of Ole Sigmund, that you have these rotating squares. And again, the only easy way of deforming it, so this is black squares are sort of rigid materials, the white materials is something very compressible, and these act as hinges, basically. And so the only easy deformation there is one of dilation. And then I thought, oh, well, this is surely a material that can't be achieved by a laminate type construction. And then I should, okay, I'll get back to that. And you can sort of extend these sort of ideas to 3 dimensions as well. And so you've got this sort of structure here, and things rotate so that the points here always form a square, and you can sort of tile a cube with those. And the group of Martin Wegner actually simplified the geometry a little bit and built it at a very low scale and small scale, and did some tests, and this actually had a Poisson's ratio of about -0.8, and ideally this material should have one of -1. Anyway, this is the structure, the laminate structure, that actually has this negative Poisson's ratio, and you can extend it to 3 dimensions as well. But basically, the dotted material here is something which is very compressible, and this is fairly rigid, not completely rigid, because it wouldn't be able to bend at all here. But you've got this sort of chevron type structures, and so if these get pulled apart there, this point goes up, and so this basically gives you your negative Poisson's ratio, and it does quite well. So these are bounds of Shikaev and Gibiansi, that's Andrei Shikaev, and you've got their bounds are these dashed lines, and this structure follows this black line there. And so later, and Larsen, Sigmund, and Boystra did topology optimization without relying on that structure, and they got something which is sort of very similar again with these sort of chevron type elements that had negative Poisson's ratio, and then they also did experiments with that. So more generally, the elasticity properties of an anisotropic materials are realized by their tensors, and they're 4th order tensors. And so you can ask whether you can actually achieve any tensor, or more generally, because of stability, the elasticity tensor has to be positive definite and also needs to satisfy some symmetries. But the answer to that is yes again. And the key point is to identify what we call extremal materials. So this is joint work with Andrei Shikaev. And so extremal materials are those where the elasticity tensors has eigenvalues close to 0 or close to infinity. And then, in particular, in 3 dimensions, there's a class of materials that we call Pentamode Materials, where you have 5 eigenvalues close to 0 and 1 eigenvalue fairly large. And this has become quite popular, the sort of study of these materials. And so this is a different type of structure, which supports a loading. It's still a biaxial loading. It has two easy modes of deformation. If you push this, the dashed material, dotted material is compressible, and this is sort of fairly rigid here. If you push this from the sides and push it at the top, things are basically stable, at least for linear elasticity. The group of Andrew Norris was sort of interested in using these for cloaking. In Pentamode Materials are also of interest for cloaking, and they built what they called meta-water. So basically it's this sort of structure here, which is one of these sort of bimode materials with inclusions like this, and it turns out that this has the density of water and the bulk modulus of water too, and a shear modulus which is very, very small, which is like the shear modulus of water as well. And so it's basically invisible in water. So you can also have structures which supports any loading with negative determinant. In other words, if I press it from the sides and pull it in this direction, then it will be stable, it won't deform. In fact, you can replace, and then I should say, once you've got all these extremal materials, the idea is to sort of laminate the extremal materials together to get any possible elasticity tensor. But all of these extremal materials that I've discussed can actually be replaced by laminate materials. And so this is one of the bimode materials that can be obtained by laminating another bimode materials with a unimode material. So anyway, you get this sort of complicated laminate structure, and then you'll be laminating all this together, so you can actually prove that you get the entire range of elasticity tensors, which is interesting. So lastly, I wanted to talk about achieving reversal of the sign of the Hall coefficient. What's the Hall coefficient have to do with? That's if you have, say, a conducting plate and you impose a voltage here with a positive sign here and negative sign here, then electrons will flow through the, because of the voltage drop from one side to the other. But if you've got a perpendicular magnetic field, then you get a force, which is the cross product of the velocity times the cross product of the velocity and the magnetic field. And so you get a force in the transverse direction, and that pushes the electrons to the other side and taking them away from this side. So you actually get in addition to the voltage here, you get a transverse voltage, which is called the Hall voltage. And that's that can be actually used as sort of a way to sort of detect magnetic fields and things, for example. So if you actually use this elementary argument that I just mentioned, then you know, if you have electrons, they will go from this direction here and that direction there, whereas holes, if it's a semiconductor, holes would go from with a positive sign. They've got an effective positive charge, so they would go in the opposite direction, and you can check that the Hall voltage has a different sign according to that. And there's the coefficient, Hall coefficient relates the strength of the magnetic field to that voltage. So so based on that, in physics textbooks, they say that the sign of the Hall coefficient tells one the sign of the charge carrier. But actually, there's a counterexample. That's what we found. So you mix materials with a positive Hall coefficient, and you get something with a negative Hall coefficient. And so, the material we had was a composite material, and you could sort of relate this. The key point is that you actually look at the matrix valued electric field. Usually you think of an electric field as vector valued, but you can impose applied electric fields in 3 different directions, and so you get a matrix valued electric field. And the key property is that the trace of that changes sign. Whoops. Yeah. So that's sort of mathematically where the important observation, and that was joint work with Vincenzo Nessi as well. So we were interested in trying to sort of realize this Hall coefficient reversal, and we sort of Marc Brion and myself came up with a 2-dimensional version which looked like interlocking rings and chainmail. And so Marc looked on the web and found this artist, Dylan White, who he's a chainmail artist. He specializes in making chainmail. And he on his website, there was this Japanese type chainmail. It was exactly the one we were looking at. And then he said, did you think about the 3-dimensional one? And that's the one that turned out to be exactly what we needed. So this is the first few layers. This is actually a picture of his chainmail. And then extending it more, you end up with a geometry like this. And the key point is in these gaps, basically the electric field changes direction. And so if you put your whole material in those gaps, you'll get this sort of reversal of this Hall coefficient. And so actually, again, this is the group of Martin Wegner, but in particular Muammar Kadek, and I think Christian Kern realized that you could just do this with not 3 materials, just with 2 materials. And instead of having a ball between the rings, you could just have a bridge. And they actually numerically found out that the Hall coefficient changed sign. And then that was sort of very nice, because followed by tests and actually building these microstructures. So this is actually real microstructures, that this is not a computer-generated image. And then, so they did sort of tests like this for the Hall coefficient, and it did show this reversal. And then just to show the sort of easiest way to get the Hall coefficient reversed is, of course, if you take your copper thing and then you reverse the signs of the leads to measure the voltage, right? It would maybe, but you put it in a box so you don't tell someone. So, Christian realized you could do this at a microscopic level, and so this tangled web here has the property that things get reversed if you sort of untangle things. I don't know. Anyway, you can sort of things get reversed, and then he numerically tested that. That hasn't been fully tested. So, and I just mentioned, I'm not going to show the geometry, but Christian actually, much to my supply, found that hierarchical laminates could even achieve this. And hierarchical laminates having an isotropic property. And so that's, in summary, we're missing a general account for why these hierarchical laminates are so effective at achieving a broad range of properties. I mentioned that, I haven't gone into it, that it's closely affiliated with the problem of when rank 1 convexity of a function equals its quasi-convexification. So if you don't know what those mean, don't worry about it. And then if you're sort of interested, I have this paper on some open problems in the theory of composites that was sort of published recently. And Yuri has helped partly solve one of the problems, and Christian Kern with this Hall effect, another one. So anyway, thank you.